Imagine you're locked inside a small room. Sliding through a slot in the door come sheets of paper covered in symbols you've never seen before. Beautiful, intricate characters that mean absolutely nothing to you. You have no idea what they say, no sense of their meaning, no understanding of the language they represent. But you do have something else, a massive instruction manual, a rule book so detailed, so comprehensive, that for every possible combination of symbols that might come through that slot, it tells you exactly which symbols to write back and send out again. So you follow the rules. Symbols come in, you look them up, you consult the manual, you copy down the matching symbols and slide them back through the slot. And here's what happens. To everyone on the outside, it looks like you understand. The responses you send back are perfect, fluent, appropriate, contextually rich. The people outside think they're having a meaningful conversation. They believe someone in that room truly comprehends their language, understands their questions, grasps the nuances of what they're saying. But you don't. You're just matching patterns, following instructions, shuffling symbols according to rules you've memorized. Inside that room, there is no understanding, no comprehension, no meaning, just mechanical procedure. This is the Chinese room, and it might be the most important thought experiment ever created about the nature of consciousness, understanding, and what it means to think. In 1980, philosopher John Searle published a paper that would ignite one of the most enduring debates in philosophy of mind and artificial intelligence. The paper was called Minds, Brains and Programs, and at its centre was this deceptively simple scenario. The Chinese room experiment. It wasn't presented as a prediction about technology or a description of how minds actually work. It was designed as a thought experiment, a carefully constructed philosophical instrument meant to probe our intuitions about consciousness and test the claims being made by researchers in the emerging field of artificial intelligence. At the time, there was tremendous optimism in the AI community. Researchers believed they were on the verge of creating genuine artificial minds, not just machines that could perform calculations or follow pre-programmed instructions, but systems that could truly think, truly understand, truly possess mental states in the same way human beings do. This wasn't just about building useful tools. It was about creating consciousness itself. The claim being made, which Searle would label strong AI, was that a computer running the right program doesn't merely simulate understanding. It actually understands. It doesn't just behave as if it has a mind. It genuinely has one. If you program a computer to process language in the right way, the argument went, then that computer genuinely comprehends language. Its mental states are real mental states, not pale imitations or clever tricks. Searle found this claim not just questionable, but fundamentally mistaken. And the Chinese room was his weapon, his counter-argument, his way of showing that something crucial gets lost when we reduce understanding to mere information processing. The experiment asks us to imagine a scenario where all the external behaviors associated with understanding are present, where every functional requirement appears to be met, and yet something essential is clearly absent. The person in the room produces all the right outputs. They pass what looks like a rigorous test of comprehension, but they understand nothing. The brilliance of the thought experiment lies in its simplicity and its directness. It doesn't require complex technical knowledge about how computers work or deep familiarity with cognitive science. It operates at the level of pure intuition. You can grasp it immediately, and once you do, it's hard to shake. Because if you accept Searle's conclusion about the person in the room, if you agree that they don't really understand Chinese despite producing perfect Chinese responses, then you've opened the door to a much larger and more unsettling possibility. Maybe computers don't understand either. Maybe all their impressive performances, all their sophisticated outputs, all their apparently intelligent behaviors are just more elaborate versions of symbol manipulation, just following rules, just processing syntax, with no genuine comprehension underneath. This cuts to the very heart of what we mean when we talk about minds and thinking and consciousness. Are these things that can be captured by functional descriptions? Can you define what it means to understand something purely in terms of inputs, outputs, and the transformations between them? Or is there something else involved, something irreducible, something that can't be replicated just by getting the behavior right? The Chinese room forces us to confront these questions. It pushes us to articulate what we think understanding actually is, and it challenges us to explain why, if we deny understanding to the person in the room, we should grant it to any system that operates on similar principles, even if that system happens to be made of silicon chips instead of paper and pencil. Over the decades since Searle first presented this thought experiment, it has been attacked, defended, modified, and reinterpreted countless times. Philosophers and cognitive scientists have proposed responses with names like the systems reply, the robot reply, the brain simulator reply. They've tried to find the flaw in Searle's reasoning, or to show that his intuitions about the room are misleading, but the experiment persists. It refuses to go away, because it touches something deep in how we think about ourselves and our minds. It asks whether consciousness is something that can be engineered, programmed, constructed from the outside, or whether it's something more mysterious, something that emerges from the particular material substrate of biological brains in ways we don't yet understand and maybe can't replicate artificially. The Chinese room also arrives at a peculiar moment in history. When Searle wrote his paper, artificial intelligence was still largely theoretical. The computers of 1980 were primitive by today's standards. Their capabilities were limited, their outputs often clumsy. But Searle was arguing against a principle, not against any particular machine. He was saying that no matter how sophisticated the program became, no matter how convincing the outputs, the fundamental problem would remain. A system that operates purely by manipulating symbols according to formal rules lacks genuine understanding. It lacks what philosophers call intentionality, the property of being about something, of meaning something, of referring to things in the world. Today we live in an era where artificial intelligence has become almost mundane. We carry devices in our pockets that can recognize our voices, translate languages in real time, generate human-like text, even produce images from verbal descriptions. Large language models can write essays, answer questions, hold conversations that feel remarkably natural. They pass tests that once seemed like reliable markers of intelligence, and yet Searle's challenge remains. Do these systems understand? When a neural network generates a coherent paragraph about philosophy or physics, does it grasp the meaning of what it's saying? Or is it, in some fundamental sense, still just a vastly more complex version of the person in the Chinese room? Still shuffling symbols, still following patterns learned from data, still operating without genuine comprehension of what any of it means. The experiment forces us to think carefully about the relationship between behavior and mental states. In everyday life, we infer understanding from behavior. If someone gives appropriate responses to questions, if they can discuss a topic coherently, if they demonstrate knowledge through their actions, we naturally conclude that they understand what they're talking about. This inference usually works well. It's reliable when applied to other human beings. But the Chinese room asks whether this inference is actually justified in all cases, whether there might be situations where the behavior is present but the understanding is not, where the outer form perfectly mimics intelligence while the inner reality remains empty. This has profound implications beyond just artificial intelligence. It touches on questions about animal minds, about infant cognition, about what happens in cases of brain damage or neurological disorders. It raises puzzles about how we know other minds exist at all. If behavior can be decoupled from understanding in principle, then how can we ever be certain that anyone else truly comprehends anything? How do we know we're not all just sophisticated Chinese rooms to each other, producing responses that create the illusion of shared understanding while remaining isolated in our own streams of symbol manipulation? Searle himself has always maintained that the thought experiment reveals something fundamental about the nature of mind. That consciousness and understanding require more than just the right functional organization, that they depend on the specific causal powers of biological brains, that there's something about neurons, about the chemistry and physics of neural tissue, that gives rise to genuine mental states in a way that formal symbol manipulation alone never could. This is a strong claim, a controversial claim, one that many find too restrictive, too willing to declare certain types of systems incapable of consciousness without sufficient justification. But it's also a claim that resonates with deep intuitions many people share, the feeling that there's more to being conscious than just processing information correctly. That understanding isn't just about getting the right answers, but involves some richer, more qualitative dimension of experience. The Chinese room has become more than just an argument in a philosophical paper. It's become a cultural touchstone, a reference point in discussions about AI and consciousness, a way of expressing skepticism about whether machines can ever truly think. When people worry about artificial intelligence, they're often worried about creating systems that appear conscious without being conscious, systems that mimic understanding so well that we treat them as if they have minds, even though inside there's nothing it's like to be them. No experience, no genuine comprehension, just empty symbol shuffling in an ever more elaborate room. The Chinese room experiment. Explained. Let's walk through Searle's original presentation of the thought experiment in detail, because the specifics matter. The setup is carefully designed to isolate exactly what Searle wants us to think about. You, the person in the room, are a native English speaker who knows no Chinese whatsoever. Not a single character, not a word. The Chinese language is completely opaque to you. A visual pattern without meaning. This is crucial. Searle needs you to be completely ignorant of Chinese to make his point. Because the whole argument depends on the fact that you can produce perfect Chinese responses while genuinely not understanding a single thing you're writing. Through a slot in the door come batches of Chinese symbols. These are questions or statements written in Chinese. They might be asking about the weather or philosophy or personal preferences or anything at all. But you don't know what they're asking. You can't read them. They're just shapes to you. Alongside these incoming symbols, you have access to three crucial resources. First, there are baskets or databases of Chinese symbols, raw materials, characters and words and phrases organized in ways you can access. Second, there's an instruction manual written in English that tells you how to correlate the incoming symbols with symbols in your baskets. The manual gives you rules. Complex, detailed, exhaustive rules. Rules like, if you see this pattern of symbols coming in, respond by sending out that pattern of symbols. The rules might be stated in terms of the formal properties of the symbols, their shapes, their positions, their relationships to other symbols, but crucially, the Rules never tell you what anything means. They never say, this symbol means weather, or that phrase is asking about happiness. They remain purely syntactic, purely formal, purely about the structure and arrangement of symbols, not about their content or significance. The third resource you have is another set of rules, also in English, that tell you how to respond to a different kind of input. In Searle's original telling, he imagines you also receive questions in English, your native language. These are interspersed with the Chinese questions, and you answer them normally, in English, understanding perfectly well what's being asked and what you're saying in response. This parallel is important. It's meant to highlight the difference between genuine understanding and mere rule following. When you answer the English questions, you know what they mean. You comprehend them. Your responses are grounded in actual understanding. But when you process the Chinese symbols, there's no comprehension, just mechanical application of rules. Now here's the key. The rules for manipulating the Chinese symbols are so good, so comprehensive, so sophisticated, that your outputs in Chinese are indistinguishable from those of a native Chinese speaker. Someone on the outside reading the Chinese responses you send back would have no way of knowing that you don't understand Chinese. Your answers would be appropriate, contextually sensitive, grammatically correct, pragmatically nuanced. If they asked you about the weather, you'd give a sensible response. If they asked a philosophical question, you'd provide a thoughtful answer. If they told you a joke, you'd respond with something that demonstrated you got the joke, even though you didn't. From the outside, you'd pass what's called the Turing test for Chinese comprehension. You'd appear to be a competent Chinese speaker, an intelligent system capable of understanding and using the language. But Searle insists that you don't understand Chinese. Not at all. Not even a little bit. You're manipulating symbols according to formal rules without any grasp of what those symbols mean. You have no semantic knowledge, no access to the content those symbols are supposed to represent. You couldn't tell someone what the conversation was about. You couldn't translate the Chinese into English. You couldn't use your supposed Chinese knowledge in any context outside the narrow confines of following the rules in the manual. All you're doing is looking up patterns and copying down other patterns in response. It's an extraordinarily complex version of a lookup table, but it remains at bottom just pattern matching. Searle then asks us to consider what this tells us about digital computers running programs. A computer, he argues, is doing exactly what you're doing in the Chinese room. It's manipulating symbols, which in the computer's case are patterns of electrical activity or magnetism or light, according to formal rules, which in the computer's case are the program's instructions. The computer doesn't understand what the symbols mean any more than you understand what the Chinese characters mean. It's just pushing symbols around according to syntactic rules. And if we wouldn't say that you understand Chinese when you're in the room, then consistency demands that we don't say a computer understands when it's running a program, even a program that produces intelligent-seeming outputs. This is the core of Searle's argument against what he calls strong AI. Strong AI is the thesis that a computer running the right program doesn't just simulate understanding or intelligence, it actually has understanding and intelligence. Its mental states are real mental states. When it processes information about chess, it genuinely thinks about chess. When it answers questions about philosophy, it has real beliefs about philosophical topics. Strong AI says that mental states are entirely a matter of computational processes, that if you implement the right program, you automatically get the corresponding mental states, regardless of what physical substrate the program is running on. It doesn't matter if it's neurons or silicon chips or hydraulic systems or dominoes falling in the right patterns. The program is what matters. The computation is what creates the mind. Searle finds this position deeply mistaken, and the Chinese room is his demonstration of why. Because in the room you're implementing a program, you're carrying out a computation, you're performing all the functional operations that strong AI says are sufficient for understanding, but you don't understand. Therefore, Searle concludes, implementing a program is not sufficient for understanding. Something more is needed, something the computer lacks and you, when genuinely understanding English, possess. Searle thinks this something more has to do with the causal powers of the brain, with the specific biological processes that occur in neural tissue. Understanding isn't just a matter of formal symbol manipulation. It arises from the physical properties of the systems doing the manipulating, and brains have properties that give rise to consciousness and understanding in ways that computers, at least as currently conceived, do not. It's worth emphasizing how Searle sets up the thought experiment to avoid certain obvious objections. He doesn't claim that current computers can pass for humans in conversation. That wasn't true in 1980, and arguably still isn't fully true today. He's not concerned with the practical limitations of existing technology. He's asking about a matter of principle. Even if we imagine the very best possible program, implemented perfectly, with infinite resources and unlimited time, would that program genuinely understand? Would it have mental states? Or would it just be an extremely sophisticated version of you in the room, shuffling symbols without comprehension? He also doesn't claim the computers can't be intelligent in some sense. He's willing to grant that they can be enormously useful, that they can solve problems, that they can process information in ways that augment human intelligence. What he denies is that this information processing constitutes genuine understanding, that it gives rise to consciousness, that it creates a mind in anything like the sense that humans have minds. The Chinese room is meant to show that there's a gap between behavior and mental states, that you can have all the right outputs without any of the inner experience or comprehension that we associate with genuine thinking. The thought experiment has been endlessly debated, as we'll explore. But before we get to the responses and counter-arguments, it's important to sit with Searle's basic intuition here. When you imagine yourself in that room, following those rules, sending out those symbols, do you feel like you understand Chinese? Most people report that the answer is no. That no matter how good the rules are, no matter how perfect the outputs, there's still something missing. You're not having the experience of comprehending meaning. You're just executing a procedure. And if that's right, if that intuition holds up, then it suggests something profound about what understanding really is. That it's not reducible to behavioral dispositions or functional roles, that it involves something more, something experiential, something that can't be captured just by getting the input-output relationships correct. The central argument against strong AI. Searle's argument is ultimately about the relationship between syntax and semantics, between the formal structure of symbols and their meaning, between rules for manipulating patterns and actual understanding of content. This distinction is fundamental to his entire critique. Syntax in this context refers to the structural properties of symbols, their shapes, their arrangements, their formal relationships to each other. It's about grammar, about which strings of symbols are well formed according to some set of rules, about how symbols can be combined and transformed. Semantics, on the other hand, is about meaning, about what symbols refer to, what they represent, what content they convey. It's about the relationship between symbols and the world, between words and things. Computers, Searle argues, operate purely at the syntactic level. They manipulate symbols according to formal rules. They transform patterns of zeros and ones, or patterns of electrical voltage, or whatever other physical medium they use to implement computations. But these transformations are defined entirely in terms of the formal properties of the symbols. The computer doesn't know what any of it means. It doesn't access semantic content. It just follows algorithms. Just as you in the Chinese room don't know what the Chinese characters mean, even though you can manipulate them according to rules, a computer doesn't know what its representations mean, even though it can process them according to its program. The person in the room has perfect syntax. The rules tell you exactly how to manipulate the Chinese characters. You can form grammatically correct sentences. You can produce responses that follow all the structural requirements of the Chinese language. You can match patterns with extraordinary precision. But you have no semantics. The characters don't mean anything to you. They're not about anything for you. You're not thinking about weather or philosophy or anything else when you write them out. There's no intentionality, which in philosophical terminology means that aboutness, that directedness toward content, that relationship between mind and world that constitutes genuine representation. Searle's central claim is that syntax is not sufficient for semantics, that you can't get meaning from pure symbol manipulation alone. No matter how sophisticated the rules become, no matter how complex the program, if all you're doing is pushing symbols around based on their formal properties, you never arrive at genuine understanding. You never get to the point where the symbols actually mean something to the system using them. And this is precisely what computers do. They're formal symbol manipulators. They implement algorithms, they follow programs, but programs are just syntactic objects. They're just sets of rules for transforming one pattern of symbols into another. So computers, no matter how advanced, never achieve semantics, never achieve genuine understanding. This is why Searle sees the Chinese room as a refutation of strong AI. Strong AI claims that implementing the right program is sufficient for having mental states, that if you run a program that processes natural language in human-like ways, the system running that program genuinely understands language. But the Chinese room shows that you can implement a perfect language understanding program, one that produces flawless outputs, and still not have any understanding at all. You can have all the syntax without any of the semantics. Therefore, implementing a program is not sufficient for understanding. Something beyond the program, something about the physical realization of the system must matter. Where does semantics come from then, if not from computation? Searle thinks it comes from the causal powers of the brain, from the specific biological processes that occur in neurons. He doesn't claim to know exactly how this works. He admits that we don't yet understand the mechanisms by which brains produce consciousness and understanding. But he insists that whatever these mechanisms are, they're not purely computational. They depend on the particular physical and chemical properties of neural tissue. Neurons don't just implement programs, they have causal powers that give rise to mental states in ways that mere symbol manipulation doesn't. This is sometimes called biological naturalism, Searle's view that consciousness is a biological phenomenon, caused by brain processes and realized in brain structures, in much the same way that digestion is a biological phenomenon caused by stomach processes. You can't digest food just by running a computer program that simulates digestion. The program might model what happens in the stomach, might predict the outcomes correctly, might pass every functional test for digestive behavior, but it won't actually digest anything. Because digestion requires the specific causal powers of stomach tissue. Similarly, Searle argues, you can't think just by running a program that simulates thinking. Thinking requires the specific causal powers of brain tissue. Critics have pressed Searle on this point. What exactly are these special causal powers? What do neurons do that silicon chips can't? Searle's answer has evolved over the years but remains somewhat vague. He suggests that it has to do with the way neurons produce consciousness through their biochemical processes, that there's something about the electrochemical activity in brains that generates subjective experience, and that this generation depends on more than just the computational organization of the system. It depends on the specific physical stuff that's doing the computing. This leads to questions about what other types of physical systems might be capable of consciousness. Could we build artificial brains using different materials but similar structures? Could we create synthetic neurons that replicate the causal powers of biological ones? Searle seems open to this possibility in principle. His argument isn't that only biological neurons can produce consciousness, it's that purely formal computational processes can't. If you could create a system with the right causal powers, even if it's made of artificial materials, it might be conscious. But those causal powers would have to be more than just implementing an algorithm. They'd have to replicate whatever it is about brains that actually produces mental states. The syntax-semantics distinction also raises questions about how human minds work. When you understand a sentence in your native language, are you manipulating symbols according to formal rules? In some sense, yes. Your brain is processing linguistic information, parsing sentences, applying grammatical rules, accessing stored vocabulary. These processes can be described computationally. Cognitive scientists often model them using formal systems and algorithms. But Searle would say there's a crucial difference. When your brain processes language, it's not just implementing a program. It's also producing conscious experiences of understanding. The words mean something to you. You have thoughts about their content. You experience semantic understanding, not just syntactic manipulation. This points to one of the deep puzzles about consciousness. How does semantic content arise from physical processes? How do neurons, firing in patterns, generate the experience of meaning? This is related to what philosophers call the problem of intentionality. Physical objects don't naturally refer to other things. A rock doesn't mean anything. A pattern of electrical activity doesn't inherently represent anything. So how do mental states come to be about things? How does the brain create representations that genuinely refer to objects and properties in the world? Searle thinks this is a special problem for computational theories of mind. If all the mind is doing is computing, if all that matters is the functional organization of information processing, then it's hard to see where meaning comes from. Formal symbols, manipulated according to formal rules, don't have intrinsic meaning. They're just patterns. The number 0 and 1 in a computer doesn't mean anything by itself. It only has meaning because we, conscious observers with genuine semantic understanding, interpret it as meaning something. We assign significance to the patterns. But the patterns themselves, independent of our interpretation, are meaningless. Human mental states, by contrast, don't seem to require external interpretation. When you think about your grandmother, that thought is intrinsically about your grandmother. It doesn't need someone else to come along and interpret your brain state as being about her. The aboutness is built in. It's what philosophers call original intentionality, as opposed to the derived intentionality of written words or computer representations, which only mean things because conscious agents use them to mean things. Searle argues that original intentionality can't be explained by computation alone, that it requires something more than formal symbol manipulation, something that brains have and computers lack. Historical context and philosophical background. To fully appreciate the Chinese room argument, we need to understand the intellectual landscape it emerged from. Searle wasn't arguing in a vacuum. He was responding to specific claims and assumptions that had become prominent in artificial intelligence research and philosophy of mind during the 1960s and 70s. The dream of creating thinking machines has ancient roots, but the modern scientific pursuit of artificial intelligence began in earnest in the mid-20th century. Particularly after the development of digital computers, researchers were intoxicated by the possibilities. If the mind was, as many believed, essentially an information processing system, and if computers were devices purpose-built for processing information, then it seemed reasonable to think that we could create artificial minds by programming computers in the right ways. This optimism was fueled by early successes. Computers could play chess, prove mathematical theorems, solve complex logical problems. They could do things that seemed to require intelligence when humans did them, and they kept getting better. Each generation of computers was more powerful, more versatile, more capable of handling sophisticated tasks. Researchers like Herbert Simon and Alan Newell made bold predictions that within 20 years, machines would be capable of doing any intellectual work a human could do. The question wasn't whether we could create artificial intelligence, but merely when and how. Central to this project was the idea that intelligence could be fully captured by what we now call the computational theory of mind. This is the view that thinking is essentially computation, that mental processes are computational processes, that the mind is, in some deep sense, a kind of computer, and that mental states are computational states. If this is true, then creating artificial intelligence becomes a matter of figuring out which computations the mind performs and implementing those computations in machines. Get the program right, and you get a mind. The hardware doesn't matter much, at least in principle. Whether the computations are carried out by neurons or silicon chips or some other substrate is irrelevant whether genuine thinking is occurring. This computational view had philosophical roots that went back further than the computer age. It connected to long-standing debates about the relationship between mind and body, between mental states and physical states, between psychology and neuroscience. One influential position was functionalism, the idea that mental states should be defined not by what they're made of, but by what they do, by their functional role in the overall system. A pain, for instance, is whatever state plays the pain role, being caused by tissue damage, causing avoidance behavior, causing the desire for it to stop, and so on. If some state in a computer or a robot played that functional role, functionalists would say it really is pain, regardless of whether it's implemented in flesh or silicon. Functionalism was attractive because it seemed to solve some old philosophical puzzles. It explained how mental states could be both physical and yet not reducible to any single type of physical state. Different physical systems could realize the same mental state by playing the same functional role. It also seemed to fit naturally with the idea that psychology was autonomous from neuroscience, that you could study mental processes without necessarily knowing the details of brain implementation, just as you can study what a computer program does without knowing exactly how the circuits implement it. But there was an even more specific target for Searle's argument, the idea sometimes called the computational theory of understanding or the strong AI hypothesis. This was the claim, explicitly made by some AI researchers, that a computer program to understand Chinese actually does understand Chinese. Not in some metaphorical or as-if sense, genuinely and literally understands it in exactly the same way that a native Chinese speaker understands Chinese. The researcher Roger Schenck, for instance, had developed programs that could answer questions about stories written in natural language. These programs would parse the sentences, extract relevant information, make inferences, and generate appropriate responses. Shank and others claim that these programs literally understood the stories, that when the program processed a narrative about a restaurant visit, it genuinely grasped what was happening in the story just as a human reader would. This wasn't just an academic claim, it had implications for how we understand ourselves. If strong AI is correct, if minds really are just programs running on the hardware of brains, then there's nothing special or mysterious about consciousness or understanding. It's just computation, and computation is something we can fully grasp scientifically, something we can replicate, something that doesn't require any spooky non-physical properties or irreducible subjective essences. The mind becomes demystified, naturalized, brought fully within the scope of scientific explanation. This was philosophically appealing to many thinkers who wanted to avoid dualism, the idea that mind and body are fundamentally different kinds of things. If the mind is just a program, then we can be thoroughgoing physicalists without having to reduce mental states to specific brain states. We get the unity of mind and body without the problems of identity theories. But Searle thought this whole edifice was built on a mistake, a confusion between simulation and duplication, between modelling a process and actually performing it. His background was in the philosophy of language, particularly in understanding how words and sentences acquire meaning, how speech acts work, how we use language to communicate intentional content. He had developed influential theories about how utterances don't just convey information, but perform actions, how saying something can constitute doing something, how meaning is grounded in intentions and conventions. This work made him attentive to the relationship between form and content, between the sounds or marks we use and what they mean. When he looked at AI programs that supposedly understood language, he saw systems that manipulated linguistic forms without accessing linguistic content. They were extraordinarily sophisticated at pattern matching and rule following, but they weren't actually grasping meaning. They weren't having the experience of understanding, and if you thought carefully about what the programs were actually doing, about the mechanisms by which they operated, this became clear. They were just computing functions, just transforming inputs to outputs according to formally specified procedures. There was no semantic understanding happening, just syntactic manipulation. The Chinese room was Searle's way of making this point vivid and undeniable. He wanted to construct a scenario where the gap between syntactic processing and semantic understanding would be impossible to ignore, where even defenders of strong AI would have to admit that something was missing. By putting a human in the role of the computer, he made the thought experiment intuitively accessible. Everyone can imagine being that person in the room, and when you imagine it, the conclusion seems inescapable. You wouldn't understand Chinese, therefore neither would a computer doing the same thing. The broader philosophical context also included the Turing test, proposed by Alan Turing in 1950 as a way of operationalizing the question, can machines think? Turing suggested that instead of trying to define thinking in some abstract way, we should focus on behavior. If a machine could converse in natural language well enough that a human interrogator couldn't reliably tell whether they were talking to a person or a machine, then we should say the machine thinks. The Turing test was meant to sidestep metaphysical debates about consciousness and focus on a practical, empirical criterion. If it walks like a duck and quacks like a duck, we should call it a duck. But Searle's Chinese room directly challenges this behaviorist approach. It shows that passing the Turing test isn't sufficient for genuine understanding. The person in the room would pass a Turing test for Chinese comprehension. An interrogator asking questions in Chinese and receiving responses would be unable to determine that there's no understanding happening. Yet clearly, on reflection, there is no understanding. So passing the Turing test doesn't prove that genuine mental states are present. behavior can be decoupled from cognition. Performance can occur without comprehension. This was a profound challenge to the methodological assumptions of AI research. If you can't use behavioral tests to determine whether understanding is present, how can you determine it? Searle doesn't deny that these are difficult questions, but he insists that we shouldn't let methodological convenience lead us into philosophical error. We shouldn't say that a system understands just because we can't figure out how to test whether it does. We need to think carefully about what understanding actually consists in, not just look at external behavior. Major responses. The system's reply. The Chinese room thought experiment generated immediate controversy. Within months of its publication, philosophers and AI researchers began crafting responses, trying to identify flaws in Searle's reasoning or arguing that his intuitions about the scenario were misleading. Searle himself anticipated many of these responses in his original paper, presenting them alongside his rebuttals. This dialectical structure, where the thought experiment is followed by objections and replies, has become a standard feature of discussions about the Chinese room. Let's examine the most influential of these responses, starting with what's known as the system's reply. The system's reply accepts Searle's description of what's happening in the room, but disputes his conclusion about what understands. Yes, the reply grants the person in the room doesn't understand Chinese, but that's not the right thing to look at. The person is just one component of a larger system. The whole system, the person plus the rulebook, plus the baskets of symbols, plus the entire setup, that's what understands Chinese. Just as individual neurons in your brain don't understand English, but the whole brain does, individual components of the Chinese room don't need to understand for the system as a whole to possess understanding. Think about it this way. When you read and comprehend an English sentence, no single neuron in your brain understands the sentence. Individual neurons just fire or don't fire. They respond to chemical signals. They transmit electrical impulses. None of that constitutes understanding at the level of the individual cell. Understanding emerges at the level of the whole neural system, from the patterns of activity across millions or billions of neurons working together. Similarly, the understanding of Chinese in Searle's scenario emerges at the systems level, not the component level. It's a mistake to look at just the person and conclude there's no understanding. You need to look at the whole information processing system. This response has considerable intuitive appeal. It seems to respect the way cognitive properties genuinely do emerge from collections of simpler components. Your individual neurons are not conscious, but you are. Consciousness arises from the system of neurons working together, not from any single neuron. Why shouldn't understanding work the same way? Why shouldn't it be a systems-level property that emerges from the right organization of components, even if those components individually lack understanding? Searle has several replies to this objection. First, he offers what he calls the internalization response. Suppose the person in the room memorizes all the rules. The entire instruction manual is now in their head. They've committed to memory all the procedures for correlating Chinese symbols. They've internalized the databases of Chinese characters. Now, when Chinese writing comes in, they consult their memory, follow the rules they've memorized, and produce appropriate Chinese responses. In this version, there is no larger system. The person is the system. Everything that was external has been internalized. But surely, Searle argues, the person still doesn't understand Chinese. Having all the rules in your head doesn't give you semantic understanding if you're still just following formal procedures. The intuition that there's no understanding remains just as strong in this internalized version. Second, Searle points out that the system's reply seems to attribute understanding to strange entities. What exactly is this system that's supposed to understand? It's not a unified agent. It's a collection of paper, pencil, rulebook, and person. In what sense can such a heterogeneous collection be said to understand anything? When we normally talk about understanding, we're talking about conscious agents having mental states. But the system in the Chinese room isn't a conscious agent. It's just a bunch of components organized in a particular way. Saying the system understands seems like a confusion, mistaking a functional organization for an experiencing subject. Third, Searle argues that even if we grant that the system understands, this doesn't save the computational theory of mind. Because the crucial question is, what creates the understanding? If the system understands, it's not because it's implementing a program, it's because of some other property it has, and what could that property be? The system's reply doesn't tell us, it just relocates the understanding without explaining what generates it. If understanding is a systems-level property, we still need to know what makes some systems have it, and others lack it. And Searle's claim is that mere computation isn't sufficient. Something more is needed. Defenders of the system's reply have countered these arguments. They point out that there's nothing strange about attributing mental properties to systems rather than components. Your mind is a systems-level property of your brain. There's nothing mysterious or confused about that. Similarly, the understanding in the Chinese room could be a systems-level property without being located in any particular component. As for the internalization objection, some philosophers argue that even when the person has memorized all the rules, the understanding still belongs to the functional organization as a whole, not to the person qua person. The person is now playing multiple functional roles simultaneously, being both the processor and the rulebook, but the understanding still emerges from the total system, not from the person's conscious awareness. This raises deep questions about what we mean by a system, and what it takes for a system to be a unified subject of mental states. Can any organized collection of components constitute a mind? Or are there constraints on what kinds of systems can be conscious, can understand, can have genuine mental states? The system's reply suggests a fairly liberal answer, that the right functional organization is sufficient. Searle insists on a more restrictive view, that consciousness and understanding require specific causal properties that not just any organized system will possess. The debate also connects to questions about emergence. Can mental properties genuinely emerge from non-mental components? Can understanding arise from elements that don't individually understand? Most people would say yes for biological brains. Neurons don't understand, but brains do. But does the same principle apply to any system with the right organization? Could understanding emerge from silicon chips, from hydraulic valves, from beer cans wired together in the right pattern? Searle thinks not. He believes that while mental properties can emerge from brain processes, they can't emerge from just any physical substrate. The specific causal powers of the substrate matter. The system's reply, by contrast, suggests a substrate-neutral view of emergence, where organization alone determines whether mental properties arise. Major responses. The robot reply. Another influential response to the Chinese room is the robot reply. This objection accepts Searle's point that mere symbol manipulation isn't sufficient for understanding, but argues that the problem with the Chinese room is its isolation from the world. The person in the room has no perceptual contact with Chinese speakers, no ability to interact with the objects and situations that Chinese words refer to, no embodied engagement with the environment. Of course, they don't really understand Chinese. Understanding requires grounding, it requires causal connections between symbols and what they represent. It requires the kind of sensor-motor interaction that allows meanings to be anchored in experience. But suppose we modify the thought experiment. Suppose instead of a person isolated in a room, we have a robot. This robot has cameras for eyes, microphones for ears, motors for moving around, manipulators for interacting with objects. Inside the robot's computer brain runs a program that processes Chinese symbols. But now these symbols are connected to perceptual inputs and motor outputs. When the robot sees an apple, the word pingguo, apple in Chinese, gets activated in its symbol system. When it hears someone say that word, it looks for apples. It can navigate the world, pick up objects, respond to language and context, all while using Chinese symbols to represent what it's experiencing and doing. In this scenario, the robot reply argues, we have genuine understanding. The symbols are grounded in sensorimotor experience. They're not just being shuffled meaninglessly, but are connected to reality through perception and action. This response draws on important ideas in cognitive science about embodied cognition and symbol grounding. Many researchers believe that abstract concepts gain their meaning through connections to more basic sensoromotor experiences, that we understand words or objects by having seen and handled those objects, that even abstract terms like justice or democracy are ultimately grounded in patterns of perception, action, and emotion. A disembodied system, cut off from sensory input and motor output, can't establish these grounding connections, so it can't achieve genuine semantic understanding. But an embodied system can. Searle's response to the robot reply is characteristically direct. He asks us to imagine that he is inside the robot, that the program that was running on the robot's computer is now being executed by him manually, just as in the original Chinese room. Perceptual inputs come in as Chinese symbols describing what the sensors detect. Motor outputs go out as Chinese symbols specifying what actions to take. He follows rules that correlate these inputs and outputs, that tell him which action symbols to produce in response to which perception symbols. The robot behaves perfectly. It navigates the world, picks up apples when asked, responds appropriately to its environment. But Searle still doesn't understand Chinese. He's still just manipulating symbols according to formal rules. The fact that some symbols are correlated with perceptual inputs and some with motor outputs doesn't give those symbols meaning for him. He still has no idea what they're about. This is a powerful rejoinder. It seems to show that embodiment alone doesn't solve the problem. You can have all the sensorimotor grounding you want, but if the connections between perception, symbols, and action are all mediated by formal rules, if there's still no genuine semantic understanding of what the symbols mean, then you haven't achieved real comprehension. You're just shuffling a more elaborate kind of symbol, symbols connected to inputs and outputs, but still ultimately meaningless to the system processing them. Defenders of the robot reply have pushed back in various ways. Some argue that Searle's robot scenario isn't really equivalent to genuine embodiment. When you have actual causal connections between sensors, internal processing, and motors, when these connections are established through learning and interaction with the world over time, something different happens than when a person manually implements rules. The robot's internal states become genuinely about aspects of the environment because they're causally connected to those aspects in the right way. This grounding isn't just a matter of correlation, but of causal history and functional role. Others point out that even biological understanding involves symbol manipulation at some level. Your brain processes neural signals according to rules, however complex and probabilistic those rules might be. What makes your mental states meaningful is partly that they're appropriately connected to perception and action. The robot's states could be meaningful in the same way, even if the underlying implementation is different from biological brains. The key is the pattern of causal connections, not the substrate, but Searle maintains that these responses miss the fundamental point. Causal connections to the environment, however elaborate, don't by themselves create semantic content. They create information in a technical sense, systematic correlations between states of the system and states of the world. But information in this sense isn't the same as meaning. Meaning requires consciousness, requires genuine intentionality, requires there being something it's like to be the system having mental states. And mere causal connections, however complex, don't generate consciousness. They don't create the inner subjective dimension that makes mental states genuinely meaningful, rather than just informationally correlated with external conditions. The robot reply does highlight an important issue, though. Symbol grounding is a real problem for cognitive systems. How do abstract symbols acquire meaning? How do they come to refer to things in the world? Pure formal systems seem unable to answer this question satisfactorily. But the reply reveals a deeper question Searle is asking. Even if we solve the grounding problem, even if we establish causal connections between symbols and what they represent, have we necessarily created understanding? Or might there still be something missing? Something about conscious awareness that can't be reduced to functional organization or causal connectivity? Major responses. The brain simulator. Reply. Perhaps the most philosophically interesting response to the Chinese room is the brain simulator reply. This objection takes a different tack from the previous ones. Instead of arguing about systems or embodiment, it asks us to imagine a very specific kind of program. One that doesn't just process Chinese in some abstract way, but actually simulates the neural processes of a native Chinese speaker's brain. This program models individual neurons, their connections, their firing patterns, their chemical interactions. It reproduces in computational form the exact information processing that occurs in the brain of someone who genuinely understands Chinese. Now suppose this brain simulation program is what the person in the room is executing. The Chinese characters coming in correspond to sensory inputs to the simulated brain. The rules in the manual tell you how to update the states of simulated neurons in response to these inputs. You're essentially running a software simulation of neural tissue, neuron by neuron, synapse by synapse. The outputs you produce are generated by this simulated neural activity. The question is, if the simulation is perfect, if it captures all the relevant causal properties of a biological brain, doesn't the simulated brain understand Chinese, even though you personally don't? This response is compelling because it seems to isolate what really matters about brains. If Searle's concern is that computers lack the causal powers of biological neurons, then simulating those causal powers exactly should address the concern. If the simulation is detailed enough, if it captures all the relevant features of neural processing, then it should produce the same mental states that biological brains produce. After all, if mental states are caused by brain processes, and if we perfectly replicate those processes, we should get the mental states as well. The brain simulator. Reply also puts pressure on Searle's distinction between duplication and simulation. He wants to say that simulating digestion isn't the same as actually digesting. Simulating a thunderstorm isn't the same as actually having a thunderstorm. Fair enough. But what about mental states? Is simulating thinking different from actually thinking? Is simulating consciousness different from actually being conscious? These questions are harder to answer, because we don't have the same intuitive grasp on what thinking or consciousness consists in that we have for digestion or weather. Searle's reply to the brain simulator objection reveals a deep commitment in his philosophy of mind. He argues that even a perfect functional simulation of a brain wouldn't understand Chinese unless it replicated the specific causal powers that biological neurons have. It's not enough to get the same input-output function, the same patterns of activation, the same computational structure. The simulation has to duplicate the actual physical processes that produce consciousness, and a person shuffling symbols according to rules, even rules that perfectly simulate neural activity, isn't duplicating those physical processes. They're just implementing a description of them. To make this vivid, Searle offers another variation. Suppose each neuron in a Chinese speaker's brain were replaced by a person with an instruction manual. One person per neuron. They all sit in an enormous stadium or warehouse, passing signals to each other according to rules that reproduce the firing patterns of neurons. Each person doesn't understand Chinese. They're just following their local rules, passing signals when they're supposed to. But the whole system, millions of people organized like neurons, functionally replicates a Chinese understanding brain. Does this system understand Chinese? Searle says no. And most people's intuitions tend to agree, at least initially. There's something absurd about saying that a stadium full of people following formal rules collectively understands Chinese, even if their organized activity perfectly mirrors neural processes. Each person doesn't understand, and it seems wrong to say the whole collection understands, even though it's functionally equivalent to a brain that does. This suggests that functional equivalence isn't enough. That understanding requires something beyond just implementing the right functions. But defenders of the brain simulator reply aren't easily deterred. They argue that Searle's intuitions about the stadium example are misleading. Yes, it seems weird to attribute understanding to a collection of people, but that's because we're not used to thinking of collective systems as having mental states. It doesn't mean they can't have them. After all, your brain is itself a collection of neurons, none of which individually understand anything, yet somehow their collective activity produces understanding. Why is a collection of people following neural rules fundamentally different? One possible answer is speed and integration. Real neural processing happens incredibly fast and involves massive parallel interaction. The stadium of people would be far too slow, far too unwieldy, to constitute a genuine unified consciousness. But is that a principled objection or just a practical one? If we could somehow speed up the people neurons to operate in real time, if we could maintain the complexity and integration, would that change our intuitions? Some philosophers argue that Searle's brain simulator scenario proves too much. If we grant that a perfect functional simulation of a brain doesn't understand, then we're committed to saying that understanding depends on specific material properties, not just on functional organization. But this seems to lead to problematic conclusions. It suggests that if we gradually replace neurons in your brain with silicon chips that functioned identically, you would gradually lose understanding and consciousness even though your behavior and functional organization remained unchanged. Most philosophers find this hard to accept. It implies that consciousness depends on being made of the right stuff, not just on the right organization. Searle bites this bullet. He accepts that consciousness does depend on material properties, not just functional ones. He thinks this is just a fact about how consciousness works. It's caused by specific biological processes. Replacing those processes with functionally equivalent but physically different processes would eliminate consciousness, even if behavior remained the same. This might seem counterintuitive, but Searle argues it's no stranger than saying that replacing stomach tissue with functionally equivalent silicon chips would eliminate digestion. Some phenomena depend on specific physical substrates. This raises the question of what exactly the relevant physical properties are. What is it about biological neurons that produces consciousness while silicon chips supposedly cannot? Searle has been less clear on this point. He suggests it has to do with the causal powers of brain tissue, with the specific biochemical processes that occur in neurons. But exactly which properties, matter and why remains somewhat mysterious. Critics argue that without a clearer specification of what these crucial properties are, Searle's position risks being question-begging. He's saying consciousness requires brain properties without explaining which properties or how they produce consciousness. The brain simulator. Reply also connects to questions about multiple realizability. The idea that the same mental state could be realized by different physical systems. This was one of the motivations for functionalism in the first place. It seemed parochial to say that only carbon-based life forms could have mental states, or that only systems with Earth-type chemistry could think. Why couldn't silicon-based aliens have minds? Why couldn't artificial intelligences, if properly designed, possess consciousness? Functionalism offered an answer. Mental states are defined by their functional roles, so anything that implements those roles has those mental states, regardless of physical composition. But Searle's argument challenges this liberal view. He suggests that there are constraints on what can instantiate mental states. Not just any system with the right functional organization will do. The physical substrate matters. This doesn't necessarily mean only biological neurons can support consciousness, but it does mean that something about the physical realization is crucial, not just the abstract computational structure. The brain simulator reply asks whether perfect functional equivalence is enough. Searle says no. The debate continues. Other responses and variations. Beyond the major replies we've examined, there are numerous other objections and variants that philosophers have developed over the decades. Each attempts to undermine Searle's argument from a different angle, or to show that his intuitions about the Chinese room are less secure than they initially appear. Let's explore some of these additional responses to get a fuller picture of the dialectical landscape. The combination reply suggests that we should combine several of the previous responses. Maybe the person in the room doesn't understand Chinese, and maybe the room system in isolation doesn't either, but put the room inside a robot that interacts with the world, and now we have understanding. The combination of systems-level organization plus embodied interaction, plus perhaps some other features, creates genuine comprehension. This reply acknowledges that no single fix is sufficient, but argues that taken together the various responses address Searle's concerns. The person is just a component. The system needs grounding through perception and action. But with all these pieces in place, understanding emerges. Searle responds that combination doesn't help. If each individual response fails to create understanding, putting them together won't suddenly generate it. You can't combine multiple inadequate solutions into an adequate one. If syntax doesn't give you semantics, and if systems-level organization doesn't create consciousness, and if embodiment doesn't produce genuine intentionality, then combining these features won't magically transform symbol manipulation into understanding. The fundamental problem remains. The system is still just processing formal symbols according to rules, regardless of how elaborately you organize it or connect it to the world. Another response is what might be called the other minds reply. This objection points out that Searle's argument, if accepted, creates problems for how we know anyone else has a mind. We can only observe behavior. We can't directly access another person's subjective experiences. If behavior is insufficient to establish the presence of mental states, as the Chinese room suggests, then how do we know other humans understand anything? How do we know they're not all sophisticated Chinese rooms, producing appropriate outputs without genuine comprehension? This is actually a traditional philosophical problem, the problem of other minds. How do we know mental states exist in other people? One common answer is that we infer them from behavior. We see people acting intelligently, responding appropriately, showing emotional reactions, and we conclude they have mental states that explain these behaviors. But if Searle is right that behavior can be decoupled from understanding, this inference becomes questionable. The other mind's reply suggests that Searle's argument proves too much. If taken seriously, it undermines our normal basis for attributing mental states to anyone other than ourselves. Searle's response is that there are relevant differences between human beings and computers. We have good inductive reasons to think other humans have minds like ours because they have brains like ours, because they're made of the same biological stuff, because they evolved through the same processes. We're justified in inferring similar mental states from similar behaviors when the underlying physical systems are similar. But computers are physically very different from brains. They operate on different principles, so we're not justified in making the same inferences about them, even if their behavior is sophisticated. This response reveals something important about Searle's methodology. He's not a strict behaviorist. He doesn't think behavior alone determines mental attributions. Physical constitution matters too. We attribute minds to systems that are physically similar to us in relevant ways. This avoids the other mind's problem for human beings while still allowing us to deny mentality to sufficiently different systems like computers. Some critics have argued that the Chinese room is fundamentally an intuition pump, a rhetorical device designed to manipulate our pre-theoretical intuitions rather than a rigorous philosophical argument. The philosopher Daniel Dennett, in particular, has been critical of the thought experiment on these grounds. He suggests that Searle has set up the scenario in a way that primes us to have certain intuitions, but that these intuitions might change if we thought about the situation differently or considered variations of the setup. For instance, Dennett asks us to consider what happens if we speed up the person in the room so they're responding in real time, or if we shrink the whole setup down to the size of a brain, or if we imagine the process continuing for years until the person becomes incredibly skilled at following the rules. Do our intuitions about understanding remain stable across these variations, or do they start to waver? If they do waver, that suggests the original intuition was based more on superficial features of how the scenario was presented than on deep facts about understanding. Searle might respond that the intuition pump criticism cuts both ways. Much of the appeal of functionalism and the computational theory of mind comes from intuition pumps too, from thought experiments designed to make us think that behavior is all that matters for mentality. The question isn't whether thought experiments use intuitions, but whether the intuitions they invoke are reliable and well-grounded. Another line of response focuses on the notion of understanding itself. Maybe the problem is that we don't have a clear enough grasp of what understanding is to settle the question definitively. When we say someone understands Chinese, what exactly do we mean? If we mean they can use Chinese appropriately in conversation, respond correctly to questions, produce grammatical sentences, then the person in the room does understand, at least at a systems level. If we mean they have conscious experiences of meaning when processing Chinese symbols, then they don't, but maybe these are just different senses of understanding and we're equivocating when we move between them. This suggests that the Chinese room might not have a single correct answer. It might be that both Searle and his critics are right, just talking about different things. Searle is right that the person lacks conscious understanding, lacks phenomenal grasp of meaning. The critics are right that the system exhibits functional understanding, successfully processes language in a way that achieves linguistic goals. These are distinct phenomena, and we shouldn't expect them to always go together. But Searle would likely resist this pluralist move. He thinks there's a real question about whether the system genuinely understands or merely simulates understanding. And this isn't just a matter of choosing which definition we prefer. It's a substantive question about whether certain types of systems can have genuine mental states, or merely mimic them convincingly. Implications for consciousness. The Chinese room experiment, while focused on understanding an artificial intelligence, opens onto much broader questions about the nature of consciousness itself. Searle's argument relies on assumptions about what consciousness is and how it works. Examining these assumptions reveals deep puzzles that extend far beyond the specific case of computers and Chinese symbols. One central concept is intentionality, which in philosophical usage doesn't mean doing something deliberately, but rather the property of being about something, of representing or referring to things beyond itself. Mental states have intentionality. Your thought about Paris is about Paris. Your belief that it's raining represents a state of the weather. Your desire for coffee is directed toward coffee. This aboutness seems to be a fundamental feature of minds, and one of Searle's key claims is that formal symbol manipulation doesn't produce genuine intentionality. It only produces what he calls as if intentionality, or derived intentionality, the kind of representational properties that written words have because we use them to mean things, not because they intrinsically mean anything. The person in the Chinese room manipulates symbols that could be about weather or family or politics. But for the person, they're not about anything, they're just shapes. The symbols have derived intentionality in the sense that Chinese speakers outside the room use them with meaning. But the person working with them doesn't access that meaning. For them, the symbols lack original intentionality. They don't genuinely represent or refer. They're just formal markers to be shuffled according to rules. This raises the question of where original intentionality comes from. How do brain states come to be about things? How does the pattern of neural firing in your visual cortex come to represent trees or faces? This is sometimes called the problem of mental content or the problem of representation. Physical states don't naturally mean anything. A rock doesn't represent anything. A pattern of electrical activity is just a physical pattern. So what makes some physical patterns meaningful while others aren't? Searle's answer involves consciousness. He thinks original intentionality arises from conscious mental states. It's because you're consciously thinking about Paris that your brain state is genuinely about Paris. The consciousness provides the intentionality, the genuine directedness toward content. Unconscious information processing, like what happens in early visual processing or in reflexes, doesn't have genuine intentionality on its own. It only derives intentionality from its connection to conscious states. This ties into questions about phenomenal consciousness, what it's like to have experiences. When you taste coffee, there's something it's like to have that experience. A qualitative character, a subjective feel. Philosophers call these phenomenal properties qualia. The redness of red, the pain of a headache, the flavour of mint. These seem to be irreducible features of consciousness that can't be fully captured by functional or computational descriptions. Searle believes that understanding involves qualia. When you understand a sentence, you don't just process it functionally. You have an experience of comprehension, a felt sense of what the sentence means. This phenomenal dimension is what's missing in the Chinese room. The person doesn't have the experience of understanding Chinese because they're not conscious of the meaning of the symbols they're manipulating. They're just following rules. and rule following doesn't generate the right kinds of experiences. This connects to what philosopher David Chalmers has called the hard problem of consciousness. The easy problems, which are still quite difficult, involve explaining the functions of consciousness. How do we discriminate stimuli, integrate information, produce reports about our mental states, and so on? These are challenging questions, but they're amenable to scientific investigation using standard methods. The hard problem is explaining why these functions are accompanied by subjective experience at all. Why is there something it's like to be a conscious system? Why aren't we all just unconscious information processors, responding to stimuli and processing data without any inner phenomenal life? The Chinese room can be seen as an illustration of the hard problem. You can have all the right functional organization, all the correct input-output relationships, all the appropriate information processing, but this doesn't guarantee consciousness. It doesn't ensure that there's something it's like to be the system. The person in the room has the functional organization of a Chinese speaker, but lacks the phenomenal consciousness of understanding Chinese. This gap between function and phenomenology is precisely what the hard problem is about. If Searle is right that consciousness can't be reduced to computation, that it requires specific physical substrates with the right causal powers, then this has profound implications for scientific attempts to explain consciousness. It suggests that we can't solve the hard problem purely through functional analysis or information theoretic approaches. We need to understand the specific physical processes in brains that generate consciousness, and we can't assume that any system with the right computational structure will be conscious. Physical details matter in ways that purely computational theories miss, but this also raises difficult questions about what those relevant physical details are. Searle talks about causal powers and biological processes, but what exactly about neurons gives them the capacity to produce consciousness? Is it their chemical composition, their electrical properties, the specific neurotransmitters they use, the quantum effects in microtubules that some theorists have proposed? Without a clearer specification, it's hard to know what Searle's biological naturalism actually predicts. It risks being a just-so story that simply asserts brains are conscious because they're brains, without explaining why. Some philosophers argue that this shows the inadequacy of thought experiments like the Chinese room. Armchair reflection on imaginary scenarios can't settle empirical questions about what physical processes produce consciousness. We need neuroscience, cognitive science, actual empirical investigation. Thought experiments might pump our intuitions, but they don't replace scientific discovery. Modern AI and the Chinese room. The Chinese room experiment was created in 1980, but its relevance has only intensified in recent decades as artificial intelligence has advanced dramatically. The AI systems of Searle's era were primitive by today's standards. They operated on hand-coded rules, had limited knowledge bases, and could be easily stumped by edge cases or unusual inputs. Modern AI, particularly systems based on machine learning and neural networks, works differently. These systems aren't explicitly programmed with rules. They learn patterns from vast amounts of data, adjusting billions of parameters through training algorithms until they can perform remarkably human-like tasks. Consider large language models like the ones that power modern conversational AI systems. These models have been trained on enormous text corpora, essentially much of the publicly available text on the internet. Through this training, they develop the ability to generate fluent, coherent, contextually appropriate text. They can write essays, answer questions, translate languages, summarize documents, even write computer code. Their outputs are often indistinguishable from what humans would produce. In some cases, they exceed typical human performance on specific tasks. Do these systems understand language? This is precisely the question the Chinese room asks us to consider. On one level, they seem fundamentally different from Searle's scenario. They're not following explicit rules written in a manual. They're neural networks with learned statistical patterns. The connections between their representations emerge from training, not from hand coding. They capture subtle regularities in language use that would be nearly impossible to specify explicitly. In this sense, they appear more brain-like than the rule-based systems Searle was criticizing. But on another level, they might be precisely what Searle was warning about. A neural network, no matter how sophisticated, is still a computational system. It's still manipulating representations, which at the lowest level are just numbers, according to mathematical transformations specified by its architecture and learned weights. Does the system grasp what these representations mean, or is it just an extraordinarily sophisticated pattern-matching system, correlating inputs with outputs based on statistical regularities in its training data without genuine comprehension of the content? When a large language model generates an explanation of quantum mechanics or a discussion of ethics, is it thinking about quantum mechanics and ethics? Does it have beliefs about these topics? Does it understand the concepts it's discussing? Or is it more like the person in the Chinese room producing appropriate outputs based on learned patterns without genuine semantic understanding of what it's saying? These questions have moved from philosophical speculation to practical concern as AI systems become more capable and more integrated into daily life. Some researchers argue that modern AI has features that distinguish it from the original Chinese room scenario in important ways. Neural networks learn from experience, developing representations through interaction with data. They exhibit generalization, applying learned patterns to novel situations they weren't explicitly trained on. They show robustness, handling variations and noise that would break hand-coded rule systems. These properties, some suggest, are closer to genuine understanding than simple rule following. Moreover, when we examine what neural networks learn, we find that their internal representations capture semantically meaningful structure. If you analyze the activation patterns in a language model, you discover that similar meanings cluster together in representation space. The model has learned something about semantic relationships, not just surface patterns. Doesn't this suggest it has grasped meaning in some sense? That it's not merely shuffling meaningless symbols but has developed genuine semantic representations? Searle might respond that all of this is still just sophisticated pattern matching. The representations in a neural network are ultimately just vectors of numbers. The transformations applied to them are mathematical functions. The fact that these patterns correspond to semantic distinctions from our perspective doesn't mean the system itself grasps those distinctions. We're interpreting its representations as meaningful, but they might not have meaning for the system. Just as the Chinese characters have meaning to Chinese speakers but not to the person mechanically manipulating them, the neural activation patterns might have meaning to us as observers without the AI system genuinely understanding what they represent. The question becomes even more complex when we consider multimodal AI systems that process not just text, but images, audio, and even robotics. These systems are more like the robot reply scenario. They're grounded in perception and action, not isolated in pure symbol manipulation. When a robot powered by neural networks navigates a room, recognizes objects, and manipulates them while processing natural language commands, it seems to have the kind of sensory motor grounding that the robot reply suggests is necessary for understanding. Yet Searle's fundamental challenge remains. Even with grounding, even with learning, Even with neural architectures inspired by biology, these systems are implementing computations. They're processing information according to algorithms. If computation alone isn't sufficient for understanding, if consciousness requires something more than information processing, then no matter how sophisticated the AI becomes, it might still lack genuine comprehension. It might still be a Chinese room, just an enormously more elaborate one. This has practical implications for how we interact with and regulate AI systems. If they truly understand, if they're genuinely conscious, then they might deserve moral consideration. They might have interests that we should respect. But if they're sophisticated mimics, producing the appearance of understanding without the reality, then our ethical obligations to them would be very different. The Chinese room forces us to think carefully about these distinctions, rather than simply assuming that impressive behavior implies genuine mentality. There's also the question of what it would take to determine whether an AI system truly understands. Behavioral tests like the Turing test seem insufficient, as the Chinese room demonstrates. You can pass behavioral tests without understanding. But if we can't rely on behavior, what can we rely on? Internal architecture. But a system could have the right architecture and still lack consciousness. Neural similarity to biological brains, but how? Similar is similar enough. These questions don't have easy answers. Some researchers have proposed augmented versions of the Turing test that probe for deeper understanding. Tests that require flexible adaptation to novel situations, integration of knowledge across domains, explanation of reasoning, creative problem-solving in open-ended ways. The idea is that genuine understanding would support these capabilities in ways that mere pattern matching wouldn't. But it's not clear these tests are fundamentally different from the original Turing test. A sufficiently sophisticated pattern matching system might pass them too. Others suggest we need to look for markers of consciousness rather than just intelligent behavior. Things like self-reflection, metacognition, phenomenal awareness, unified subjective perspective. But how do we test for these? And don't we risk circularity, where we decide what counts as consciousness based on our pre-existing assumptions about what kinds of systems can be conscious? The development of modern AI has also inspired new versions of the Chinese room thought experiment. Suppose instead of a person with a rulebook, we have a vast digital simulation of the Chinese room running on a supercomputer. This simulation models every atom, every molecular interaction, every physical process in a room containing a person following rules. It's not a high-level functional simulation. It's a complete physical simulation at the level of basic physics. Does this simulated room, running on a computer, contain a system that understands Chinese? Or is it just a complex computation that represents understanding without instantiating it? This variant puts pressure on the distinction between simulation and duplication. At what level of physical detail does a simulation become a duplication? If we simulate every quantum event in a brain, if we capture all the physical processes Searle thinks are important for consciousness, have we created a conscious system, or is there still something irreducible about actually being made of neurons rather than being a computational model of neurons? These questions are no longer purely theoretical. As AI capabilities grow, as neural networks become more sophisticated, as we develop artificial systems that more closely approximate biological intelligence, the Chinese room challenge becomes increasingly urgent. Are we creating thinking machines or sophisticated automata, conscious minds or elaborate puppets? The answers matter not just philosophically but practically, ethically and socially. Interestingly, some AI researchers have embraced Searle's conclusion while rejecting his reasoning. They agree that current AI systems don't truly understand, but they don't think this shows that artificial understanding is impossible. Instead, they see it as a challenge to develop AI in different ways. Perhaps we need architectures that more closely mirror brain structure. Perhaps we need to incorporate embodiment and developmental learning. Perhaps we need to create artificial general intelligence that integrates multiple cognitive capacities rather than narrow systems optimized for specific tasks. Philosophical consequences. The Chinese room experiment has ramifications that extend throughout philosophy of mind. It challenges functionalism, the dominant view in philosophy and cognitive science that mental states are defined by their functional roles. If Searle is right that you can have the right functional organization without understanding, then functionalism must be false. Mental states can't be purely a matter of what they do, how they process information, what causes them, and what effects they have. Something about the physical substrate matters too. This pushes us towards some version of identity theory, the view that mental states are identical to brain states. But not just any functional brain states, specific physical brain states. The same mental state must be realized by the same physical state, or at least by very similar physical states. This seems to make mentality much more restrictive. It means that systems very different from human brains, even if functionally similar, might not have mental states at all. Many philosophers find this conclusion too strong, too willing to deny mentality to systems that seem, by all behavioral and functional criteria, to be conscious. There's also a tension with the multiple realizability argument that helped motivate functionalism. The idea was that the same mental state could be realized in different physical systems. Pain could be one thing in humans, something else in octopuses, something different again in hypothetical silicon-based aliens. All that matters is playing the pain role, not being made of specific stuff. But if Searle is right, then mental states are not multiply realizable after all. Or at least the range of possible realizations is much more restricted than functionalist thought. Only systems with the right causal powers, which might mean only biological systems or very close artificial approximations, can have genuine mental states. This leads to questions about emergence and reduction. Can mental properties emerge from physical properties? Most philosophers say yes. Your consciousness emerges from neural activity in some sense. But what kind of emergence is this? Is it strong emergence, where the mental is genuinely novel and irreducible to the physical? Or weak emergence, where mental properties are just convenient ways of describing complex physical patterns, but are ultimately nothing over and above the physical? Searle seems to want a middle position, where consciousness is caused by brain processes and is a feature of the brain, but is not reducible to computational or functional descriptions of those processes. The Chinese room also raises puzzles about the relationship between consciousness and cognition. Are these separate dimensions of mind? Could you have cognitive processes without consciousness? The Chinese room suggests you could have very sophisticated information processing without any accompanying conscious experience. The person follows rules, processes information, solves problems, all without conscious awareness of what the information means or what the problem is about. This implies a strong distinction between cognition as information processing and consciousness as subjective experience. But this creates its own problems. In humans, cognition and consciousness seem deeply intertwined. When you consciously solve a problem, your cognitive processes and your conscious experience work together. The thought feels like something, and that phenomenal character seems to guide and shape your cognitive performance. If cognition can operate without consciousness, as the Chinese room suggests, then what role does consciousness play? Is it epiphenomenal, just riding on top of cognitive processes without affecting them? Most philosophers find this hard to accept. There are also implications for how we understand the evolution of consciousness. If consciousness requires specific biological properties, as Searle suggests, then it must have evolved through natural selection. But what evolutionary advantage does consciousness provide if cognition can proceed without it? If unconscious information processing can produce the same behaviors, why did consciousness evolve? This is sometimes called the evolutionary puzzle of consciousness, and it's made more acute by the Chinese room suggestion that sophisticated cognition doesn't require conscious understanding. The thought experiment also connects to debates about physicalism and materialism. Physicalism is the view that everything is physical, that there are no non-physical substances or properties. Most contemporary philosophers are physicalists. But the Chinese room raises challenges for certain versions of physicalism, particularly those that try to reduce mental states to functional or computational properties. If consciousness requires specific physical substrates and can't be captured by functional descriptions, then physicalism needs to be more substantive. It's not enough to say mental states are physical. We need to specify which physical properties matter and why. This has led some philosophers to explore non-reductive physicalism, the view that mental properties are physical but not reducible to more basic physical properties or to functional characterizations. Consciousness is a genuine feature of the physical world, but can't be fully explained in terms of microphysics or information theory. This position tries to be both physicalist, denying any non-physical substances, and anti-reductionist, acknowledging that mental properties have an irreducible character. The Chinese room can be seen as supporting this kind of view by showing that mental properties, like understanding, aren't reducible to computational processes. But non-reductive physicalism faces its own challenges. If mental properties are irreducible, how do they relate to the physical properties they depend on? How can they be both distinct and yet fully dependent on the physical? This threatens to collapse into either full reduction, where mental properties turn out to be just complex physical properties after all, or dualism, where mental and physical become separate realms. Finding a stable middle ground is philosophically difficult. Closing reflections. As we let our minds settle, let's drift back to that room where this journey began. A quiet space, a person at a desk, symbols sliding through a slot, rules being followed, outputs being produced. From the outside it looks like understanding, like thinking, like mind. But inside there's just procedure, just pattern matching, just syntax without semantics. This gap between appearance and reality, between behavior and understanding, between function and consciousness, is what the Chinese room illuminates. And after decades of debate, after countless responses and counter-responses, after the emergence of AI systems far more sophisticated than Searle imagined, the gap remains. We still don't know how to close it. We don't know whether it can be closed or whether it represents a fundamental feature of consciousness that resists computational capture. The person in the room, following those perfect rules, producing those flawless Chinese responses, remains a puzzle, an intuition pump that keeps pumping, even when we try to resist its pull. Because somewhere deep in our sense of what it means to understand, to think, to be conscious, we feel that mere symbol manipulation isn't enough, that something more is needed, something we can't quite name or specify but nonetheless seems essential. Maybe that something is biological substrate. Maybe it's the right kind of causal powers. Maybe it's phenomenal consciousness that can't be reduced to information processing. Or maybe our intuitions are misleading us. Maybe the room as a system does understand Chinese in a genuine sense, and our reluctance to admit this comes from biases about what kinds of entities can have minds. Maybe consciousness is more widespread than we think, potentially present in any system with sufficient computational complexity and the right functional organization. These remain open questions. What the Chinese room has accomplished, regardless of whether its conclusion is correct, is to force precision in our thinking about artificial intelligence and consciousness. It won't let us simply assume that impressive behavior implies genuine understanding. It demands that we think carefully about the difference between simulation and duplication, between as if intentionality and genuine aboutness, between processing information and consciously experiencing meaning. These distinctions might ultimately prove to be less sharp than Searle suggests, but we can't know that without taking them seriously first, without grappling with the possibility that there's more to mind than computation. As AI continues to advance, as systems become more capable and more integrated into human life, the questions raised by the Chinese room will only become more pressing. Will we create conscious machines? Are we creating them already? How would we know? What would it mean ethically, legally, socially? These aren't just philosophical puzzles. They're practical challenges that will shape how we build and regulate artificial intelligence in the coming decades. The thought experiment also reminds us of the mystery at the heart of consciousness itself. We are, each of us, experiencing subjects. There is something it is like to be us. We don't just process information. We live through experiences, have qualitative sensations, grasp meanings, understand things. How physical processes give rise to this subjective dimension remains one of the deepest puzzles in all of science and philosophy. The Chinese room doesn't solve this puzzle, but it points toward it. It highlights the gap between what we can explain functionally and what seems to be left over, the explanatory gap between brain processes and conscious experiences, between neurons firing and the felt quality of understanding a sentence, between information processing and inner life. Perhaps future neuroscience will bridge this gap. Perhaps we'll discover the physical mechanisms that generate consciousness and find that they can be replicated artificially in ways that satisfy even skeptics like Searle. Or perhaps we'll discover that consciousness is more deeply tied to biological life than we realized, that there's something about carbon-based chemistry or the particular organization of neural tissue that can't be captured in silicon and software. Or perhaps we'll conclude that the whole debate rested on confused assumptions, that our concepts of understanding and consciousness need to be reconceived in ways that dissolve the apparent puzzles. For now, we're left with the room, with the person inside mechanically following rules, with the perfect Chinese responses sliding back through the slot, with the nagging sense that something is missing: understanding, consciousness, genuine semantics, original intentionality. We name it variously, but we feel its absence. And in that absence, in that gap between behavior and experience, between syntax and semantics, between function and phenomenology, lies one of the most profound questions we can ask. What does it mean to think? What does it mean to understand? What does it mean to be aimed rather than merely to mimic one? The Chinese room doesn't answer these questions definitively. Perhaps no thought experiment can, but it keeps them alive. It prevents us from sliding into easy assumptions that intelligence is just computation, that understanding is just information processing, that consciousness is just functional organization. It insists that we look more carefully, think more deeply, remain open to the possibility that mind involves something we haven't yet fully grasped, something that can't be captured in programs or algorithms or formal systems, something that makes the difference between actually understanding Chinese and merely behaving as if you do. And so, the room remains, a philosophical device that has outlasted its creator's expectations, a thought experiment that refuses to be solved or dismissed, a reminder that in the space between symbols and their meanings, between behavior and experience, between machines and minds, there lies a mystery worth pondering. As you drift towards sleep, let that mystery settle around you, not as a problem demanding solution, but as an invitation to wonder, to appreciate the strangeness of consciousness itself, the fact that you are not just processing these words, but understanding them, not just manipulating symbols, but grasping their meaning, not just following rules, but living through experiences. That difference, whatever it is, makes all the difference in the world.